Here's our video for lesson 5.4, solving special systems of linear equations. So all the systems we've looked at up to this point have just had one solution. We've looked at a couple different ways to solve systems of equation. So now things are going to open up a little bit. You're going to have options on how you want to solve them, and you may end up with more than one solution or no solutions at all. So let's just kind of talk real quickly about what those possibilities are and how we can solve these systems. So we looked at solving by graphing, and you're going to want to use this method when it's easy to look at an equation and graph it. So that's usually when it's in that form y equals mx plus b, because then we can pick out that y-intercept and the slope and draw a graph really easily. Substitution works really nice when I've got an equation in that form, y equals something or x equals something, then we can just substitute in. And then elimination works well when I have matching terms, and then I can add the entire equations together and make something go away. I really like elimination. Everybody's going to have their own preference for the way that you do things and what looks easiest to you. But try to be mindful of that as you're looking at these problems. What method would make your life the easiest, and use that one. The different possibilities we have are one solution. This is what we've seen up until this point. Remember, a solution to a system is an answer that makes both equations true at the same time. And on a graph, what that means is it's going to be that point of intersection, because a graph is the visual representation of all solutions. There are other possibilities, right? If we have two lines, there's only three things that can happen. They cross at one point, and we end up with one solution. Or they never cross, which is what we call parallel lines. And if you're not graphing, what you're going to end up with, if you use elimination or substitution, you're going to end up with all of the variables going away, and you're going to end up with a statement that's false, like 3 equals 0. And we saw equations with no solutions earlier in the year, and I always kind of remember it, right? If it's not true, there are no solutions. If all the variables go away and it is true, we end up with infinite solutions. And then what this will be is, it will actually be two lines that are the exact same line. It's just going to be written differently. So one equation is going to be a multiple of the other. And we'll see an example of this in just a second. Okay, so these are our three options of how we're going to solve the system and what kind of solutions we can come up with. So here we go. Example 1. Again, you could do any method you want. This might be a good place to kind of pause real quick and think about what might be easiest for you. For me, when I look at this, I'm in nice slope-intercept form. I would probably graph these, as long as I had a graphing tool to do that with. So that first equation, my y-intercept is 1. My slope is 2. So I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. And I can draw my line. So this is that first equation, y equals 2x plus 1. And my second equation, y equals 2x minus 5. Start here, and again, my slope is the same. And again, we talked about this earlier in the year too. So the better you know this stuff, you can kind of start coming up with some shortcuts. If you notice that the slope is exactly the same, you know that we either have the exact same line or those lines are parallel. So this one is y equals 2x minus 5. So we can already tell that this has no solution. They never cross. These two equations are never going to have any common solution. If we were to do this using substitution, which you could easily do. I'm going to kind of try to divide this up here. We'll do substitution over here. So I've got y equals this, and I've also got y equals that. So if I were to substitute, we would end up with 2x plus 1 equals 2x minus 5. And when we go through that solving process, we need to get all our variables to one side, all of our numbers to the other. So if I subtract 2x to get rid of the variable, we end up with 1 equals negative 5. So this is that case. All the variables went away. I have a false statement. So again, no solution. If we used elimination, this one's going to work out pretty nicely as well. I should have done that on the other side so I could just use the equations there instead of rewriting. That's okay. Y equals 2x plus 1. Y equals 2x minus 5. And I would just subtract. Y minus y is 0. 2x minus 2x is 0. 1 minus negative 5 would be 6. So we end up with 0 equals 6. And again, it's a false statement. All my variables went away. No solution. Okay, so no solution is going to look like these three things, right? Variables go away, false. Variables go away, false. Lines are parallel. Infinite solutions, as we said earlier, if it's infinite, that means we have the exact same line. You could solve this again using any method. I'm going to try to be a little smarter about it this time. Let's use elimination here. And what I'm noticing, it looks like if I multiply this by 2, I'm going to get some things that match up. So let's do that. So let's do that right down here so that we've got them stacked again times 2. We end up with negative 4x plus 2y equals 6. And now when I'm just going to cross that out because I turned that into the other one. I'm going to subtract because I've got the same values here. So we've got 0, 0, 0. Right? Everything cancels out. And that's what's going to happen because one equation is just a multiple of the other. So this is where all your variables go away and we get a true statement. Right? That's how we know that there are infinite solutions. We could do substitution. These don't really look nice to graph right away, but once we do substitution, we'll get it into that form, and it will make more sense to graph this. So this one looks fairly easy to get as x equals or y equals. If I just add 2x to both sides, you'll end up with y equals 2x plus 3. And if I substitute that into the bottom equation, you get negative 4x plus 2 times 2x plus 3 equals 6. This is probably the worst way to do this in this situation. Negative 4x, let's do our distribution. We've got 4x plus 6 equals 6. Combine like terms on the left, so I've got 4x and negative 4x, which is nothing. 6 equals 6. Again, true. Infinite solutions. So we could make both equations look like this. And you might be able to see that kind of easily if we just look at the bottom one. If we were to add 4x to both sides and then divide by 2. If you don't believe me, take just a second and do it yourself. So our y-intercept here would be 3. Our slope is 2. So that would look like this, right? Both lines would look like this. So if I graphed the second line right on, it would be right on top of that with all of the exact same points, right? infinite solutions. It's the exact same line, just written in a different way. So here's your opportunity. Please definitely pause here. Take a few minutes, try to solve these on your own. Take your time to consider which option might be the best option to use, whether that be graphing, substitution, or elimination. In this first one, what I see when I look at this right away, besides fractions, which are ugly and we don't like, I've got 4/3 y equals something. But then in this other equation, I've got that same ugly 4/3 y. So I would probably substitute. I would take this and substitute it for that 4/3 y, because I know 4/3 y is 3x minus 14. So let's do that. So we would end up with 3x plus 3x minus 14 equals -10, which is 6x minus 14 equals -10. Add 14 to both sides, 6x equals 4. Divide by 6, x equals 4 over 6, which is the same as 2 over 3. And if you punch it into a calculator and you get a decimal, it's going to be 0.6 repeating. Okay? Not the nicest answer, but it's not horrible. We can work with this. So that is our value of x, 2/3. So now I've got x, so we need to substitute this back in. I'm not seeing one that looks really a lot nicer than the other. I guess let's do... Nope, we're trying to find y, so this one will work out a little bit better, because then I've got the y on the other side. So 4/3 y equals 3 times x, that'll work out okay, minus 14. Cutting it close on room here. 4/3 y, 3 times 2/3 is 2, minus 14. Put that together, you get 4 over 3y equals -12. Now, the easiest way to get rid of this fraction times y, so think about what could I multiply this fraction by to make it a 1, because then we would have just 1y. And we've done this earlier in the year also. If I take that fraction and I flip it, we call that the reciprocal. If I multiply by the reciprocal, and I do that on both sides, next, when we multiply these fractions, I got 3 times 4 is 12, 4 times 3 is also 12. 12 over 12 is just 1. Okay? So we get y equals, don't really have a great place to write this. I guess I'll squeeze it in here down below. Y equals, and then -12 times 3 over 4. This actually does work out okay. This comes out to -9. So this is our solution to the system. And I don't think there was necessarily a greater way to do this. I don't know. I guess elimination would have worked out okay as well. We would want to maybe rearrange a little bit and then do some elimination. That could have worked out too. Okay, moving on to the second one. To me, when I look at this, this looks like a great graphing system. You could, again, substitution would work really well too, but I think if we graph this, we're going to see right away, look, they're nice slope-intercept form. They both even have the same y-intercept, just a different slope. So right away, I can probably tell if I just think about what these graphs are going to look like, this is going to have one solution. So the top equation, -2x minus 4. So my slope is -2, so now I'm going down 2 and over 1, down 2 and over 1. go. And then my second equation, positive 2x minus 4. So again, my y-intercept is here, and my positive 2x. So my line looks like this. So this is one solution, right, very nicely at 0, comma, negative 4.